Let us recall what we were doing. Uh, we stated the theorem saying let tau be a topological space on X with basis B and Y is a subset of X. Then script B suffix Y given by B intersection Y where B belongs to B is a basis for tau Y. Let us recall what is tau Y. We have stated previously what is tau Y, and we proved that tau Y is a topology which is called subspace topology. Here, so Y is a subset of X. Tau Y is defined to be Y intersection U, where U is open in tau. Alright, so let me just put up that it over here. Let's write the proof. Recall, we have tau Y, tau suffix Y is equals to that of all Y intersection U where U is open in tau, that is U belongs to tau. And now we have to show that this script by is a basis for a topology tau Y. Okay, now let's see. Let me show you how. Here, so we have the basis. We know the topology tau Y, and we have to show that this B is a basis for tau Y. So these are the two things what we have to show. We have to show that this script by is in tau Y, and for all U, this is U in tau, and for all X belongs to U, there exists Bu belongs to B such that X belongs to Bu which contains Z. These are the 2 points what we have to show right now. So let's first show that By belongs to, By is a subset of tau Y. And to show that, okay, let me write first one. To show that this By is subset of tau Y. Okay, and to show that when something is subset of other one, you have to take one element from this set and show that that element is in this set, arbitrary element, of course. Okay, so let us take some element from By, say B dash belongs to By. And remember now what is By. By is B intersection Y. So if this B dash belongs to By, that means there is some element in script B such that B dash can be written as intersection of Y and that element. Okay, so this implies, let me hide this. Okay, this implies there exists B belongs to this script B because of this, such that we can write this B dash as B intersection with Y or Y intersection B. Okay, and okay, now since this script B is a basis for topology tau, that means script B is subset of tau. Now since this script B is a subset of tau, and this B belongs to B dash. Sorry, this B belongs to B, not B dash. This B belongs to B, and B is the subset of tau. That implies this B belongs to tau. Okay, and hence we have this B dash, which we are writing as B intersection Y. So this B is the element of tau. This B is the element of tau, and you are writing B dash as B intersection Y. So obviously this B dash is open in tau Y. So this implies this B dash belongs to tau Y. So what we have done is we have taken one element from this set, that is script By, and we showed that this element B dash belongs to tau Y, and this implies this script By is a subset of tau Y. Other way around it need not hold. Okay, let us take the second point now. For the second point, Let me again take you to the definition of basis here. For all open sets in the topology tau, and if you take any element in that open set, something happens. So to check this, let us check first one open set in the space tau 1. So let us use V. So let V belongs to tau y and take one element in this V, and let us take V belongs to V, which is of course um, V. Okay, let me just write this afterwards. Okay, or if we put this Y here, I'll tell you why it is in the next steps. Now this implies V belongs to tau y means what? V is open in tau y, and if V is open in tau y, we will have some open set in tau such that V can be written as Y intersection that open set. So this implies there exists some U belonging to tau that is open in tau such that we can write V as Y intersection with U. Okay, so and that is why I said this V is contained inside Y, because V is nothing but Y intersection U, so obviously it will be a subset of Y, and that's why I've written this V belongs to V, which is contained inside Y. Okay, and of course this V also a subset of U, because V is nothing but U intersection some set, so obviously that V should be inside U. So I can write, and this V belongs to V, right, because we have taken from here, and which is contained inside again U. Let us take this as say 2. Okay, now since again we will use the fact that this B is a basis for tau. Now since this B is a basis for tau and V, this U is element of tau, and you are taking V is in U, there exists say B, let us write suffix V, BV, which belongs to the script B, such that this V will belongs to this BV, and which will contain set U. Again, I'm repeating, we are using the fact that this script B is a basis for tau, U belongs to tau, and V belongs to U, and hence by definition of basis we will have this fact. Okay, let us denote this by 3. So remember your aim. Let me go back to the definition. So what we did is we got one open set in tau y and we got one element in that open set. We have to show this now. We have to show that there exists some another element in the your basis such that x belongs to that element, and that is contained inside your U. That is the open set what you have taken. Okay, so here we are. So what will be that open set? This is the setup you can think of now. What open set you can take, or which open set you will take so that the required condition will be is possible. Okay, so you think on that and then you can proceed. So let us take this BV dash, some notation, as BV intersection with Y. Now BV we know, this is the BV, V belongs to BV, that we know, and of course V belongs to Y, that implies this V will belongs to BV intersection Y, and that implies V will belongs to B dash of V. Okay, and this you are taking one element, basic element from B, and you are taking intersection with Y. This implies this element should or will belongs to your script BY. All those points you can note it down. Okay, I'm not writing all the points. Alright, so you got one element V in this, I mean BV dash in BY dash, and as I said, this will contain V. Okay, let me write that too here. From 1 and 3, I'll take you to that. V belongs to Y, V belongs to BV, so V will belongs to BV intersection Y, and so BV belongs to BV dash. So let's put that. From 1 and 3 is V belongs to Y, and this V belongs to BV. This implies V belongs to BV, V suffix V intersection Y. This implies V will belongs to BV dash. And secondly, we have to show that this BV dash is contained inside V. That's what we have taken. We have started with. We have taken some open set V. So we have to now show that BV dash contains inside V. So we can work on that. Let me write here. You take a pause. We work on that, and then we can proceed. All right. So from 1, will that work? No. From 2 and 3. From 2 and 3, we can use these two equations and show that BV dash is contained inside V. Okay, so from 2 and 3, what we have is, oh, let me take it over. What we have is BV dash, which is in fact equals to BV intersection with Y, and this BV is contained inside, U. Alright, so this intersection will contain inside U intersection with Y, and you can check what is U intersection Y. U intersection Y is V, so this will be equals to V, sorry, capital V. This is V. That is, now what we have shown that is V belongs to BV dash, and BV dash is subset of V. That is, this V belongs to BV dash, which is contained inside V, and hence this is the second point what we have proved. Hence, the script BY is basis for the Y. So understand what we have done. Okay, let me ask 2-3 questions and we can proceed for the next concept. Answer these questions. What is the basis for a subspace topology? Remember that By is a basis for a subspace topology, tau y. Okay, so first you understand what is a subspace, and then you can go for the basis of a subspace. Right, subbasis. What is a basis for a subspace topology? On Q set of all the rationals induced by usual topology on R. So you have a usual topology on R, that's RU, and Q is a subset of RU with the defined operations QY or Q will form a subspace topology. The question is, what will be the basis for the subspace topology? Okay, you can answer that. You can check. Now, what is the basis for subspace topology said induced by usual topology and R. Okay. I remember in last concept I asked you what is the subspace topology on Z. Okay, Z is a subset of R with usual topology. And you know what are the open sets in the subspace topology? It is Y in intersection with some open set in the whole space. That is the topology. And now the question is what will be the subspace? I mean basis for the subspace topology on Z. Correct? And one more. Work on this. You know what are the open sets? Okay, so let me give an example on open sets. So let x equals to R. Let us take R with usual topology. Let tau x be equals to usual topology on R. Let us take y to be the set which is closed interval minus 1 to 1. Okay, let us take two sets now. Let A will be equals to set of all x belonging to R such that the half is less than mod x which is less than 1. This is one set. Let us identify the set. Let us take B to be set of all x belonging to R such that half is less than mod x. Now I will include 1 also. Here that 1 is not included, but now we are including 1. So first identify this set. First on the real lines, because we are dealing with in real lines, right? R, so all the real numbers. So first you draw the line and then you mark this A and B on the real line. Okay, what are the points? This A and B represents on the real line. Okay. Now the question is A and B open in Y? This question. Second is A, B open in. So you can answer these both questions, understand and clear your doubts. Alright. So let's go for the next concept, which is called a product topology. You understand this? We are going slowly. The product. That's the same thing as what we're doing in Cartesian product. So product topology. Again, you can see there is something called as cofinite topology. As I mentioned earlier, check the definition of cofinite topology and show that it's a topology on that side. Okay, cofinite topology, that is complement finite, right here. Cofinite topology. Okay, check what is the definition and prove that it's a topology on that set. Okay, this is the first one. And the second one, as as we define cofinite topology, there is something called as co-countable. Co-countable topology. Or you may have some other terminology. Here you are taking complement finite and you are taking complement countable. And there are many other definitions for the topology as well. I mean, other examples. Only thing you have to check is those three properties: empty set and the whole space should be there. Then arbitrary union of open set should be open, and finite intersection of those elements of the set should be there in that given set. Okay, so let's go for this product topology. Let me just divide this. So check this cofinite topology and co-countable topology. There's something called as K topology that also you can check. Right. So let's take two topologies first. So let x comma tau 1 and let me take y comma tau 2 be two topological basis. Okay. Let us take a set of this B as set of all U cross V. Now, from where this U will come and from where this V will come. Understand what is Cartesian product. If you don't know, please check what is Cartesian product. Right? If you don't know Cartesian product, then you can't do anything in the further part wherein the Cartesian product is involved. So check how you have how the Cartesian product is defined, how you can write Cartesian product, how you will draw the diagram of two Cartesian product. For example, you can take a subset of R cross R. Right? Of course, it will be ordered pair. One point is from here, and the second point is from here, and we write this x comma y. Okay. Check how you will draw the diagrams for some sets. Take different sets and draw the diagrams. So that exercise you can do. Okay. Now here, let us take a set of all u cross v, where u is from the first, that is x, right? This topological space, and v comes from the another topological space. So let us take this u where such that u belongs to tau 1, which is open in tau 1. This v belongs to tau 2. Okay. We know that what is tau 1, tau 2. From tau 1, you take some element, one element. From tau 2, you take one element, you take a Cartesian product of that. This cross product, it will be here. So take all those elements here. Again, you can ask if this tau 1 has say m elements, if tau 2 has n elements, how many elements this v will have? If tau 1 is countable, if tau 2 is uncountable, then is this v countable or uncountable? Those questions you can always ask. Okay. Now, what you are doing here is you are taking some u from tau 1 and v from tau 2. And tau 1 is a subset of power set of x, tau 2 is a subset of power set of y. And you are taking u cross v. So, of course, this will be a subset of power set of x cross y. So, this, if you take this set, this is a basis for topology on x cross y. Now here, if we see, we don't know what is the basis. I mean, what is the topology? But we are saying that this P is the basis for some topology on x plus y, and the topology generated by this basis is called the product topology. Okay, so first check which definition we will use, and you can proceed. Once you are done with your proof, you can come back here and verify your proof. That's how you have to study. Alright. So first point where you have to show that it's a basis is to take some element from x cross y and get one element from this basis such that this x cross y element will be in these elements. Okay, let me repeat. You take one element in x cross y first. So let now again you have to check how will be the element of x cross y. The element of x cross y will be ordered pair x comma y. Let us take one element from x cross y. You have to show that there is some element of this kind of thing such that this x comma y will be in that element and that will be subset of x cross y. Okay, and for that, let us take now what is the meaning of x comma y belongs to x plus y? This implies this x will belong to x and this y will belong to y. And for that, please excuse. Yes, all right. So, yeah. So x comma y belongs to x plus y means this x will come from x and this y will come from y. Now we have to get some basic element from this set. And what will be that element? You can think of. You have to get one element from here where first element is tau 1 and second element is in tau 2. What element will take? Okay. So what we'll do is since tau 1 is topology on x, tau 2 is topology on y, that means x belongs to tau 1, y belongs to tau 2. So since x belongs to tau 1 and y belongs to tau 2, this implies when you take x cross y, that will be the element here because you are taking x from here and you are taking y from here and you are taking the cross product of it. That means it will be here in this B. This implies x plus y is an element of B. And you have taken x comma y. This sentence is not correct. It's the over here right now. So we are not dealing with it. So and this x comma y belongs to x plus y, and of course it will be just a set of x plus y. So you are taking one point in x plus y, your whole space. You got one element. Fortunately, you got the same whole set. So you got an open set in this B. So one element in that C, basic element. So that this point is in that element and which contains the whole space. So it's the first point to show that something is a basis for a topology. Okay. Now for the second point, it says you take two open sets in the two elements. I should not use open set. Open set. So what you have to do is you take two elements from this set. You take one element in their intersection, and you have to find the third element in that this collection, such that something happens. Okay. So for that, let's take again x comma y or some p comma q. Let's take p comma q belongs to. You take two open sets. Again, I use open set. I should not use open set. Okay. So let's take two elements from here. So one element p comma q belongs to some element here, intersection some element here. Okay, and the elements in this side are nothing but u intersection v kind of things. So let's take p comma q belongs to one open set. Say again, I'm using open open set. Say u1 cross v1, and you take another. You take another. Came out. Okay, so let's take p comma q, which belongs to u1 intersection v1, and let's take another element from that set. Let's take that to be u2 cross v2. Now again, I need not say that u1 and u2 are from tau 1, v1 and v2 are from tau 2. That is understood now. If you are smart now, you should understand that now. This implies this p comma q belongs this. So this implies p comma q belongs to this set as well as p comma q belongs to this set. That implies p will belongs to u1 and p2 and p will belongs to u2. That means p will belongs to u1 intersection u2. Similarly, this q will belongs to v1 intersection v2. So this p comma q will belongs to u1 intersection u2. You can prove this if you are confused for this. Say and v1 intersection v2. Proof just now I said. And now we want to show that this and u1 intersection u2 belongs to tau 1, v1 intersection v2 belongs to tau 2. Let me ask you why. I should not tell you all the answers. You have to think on this now. Why this will belong to tau 1 and this will belong to tau 2. And if you see this, u1 intersection u2 cross with v1 intersection intersection V2 will be a subset of course, it's very simple thing. You can show them equal in some cases or always. U1 cross V1 intersection with U2 cross V2. Hence, what we have achieved is we have taken this point P comma Q, which we have taken in this, which we got that in this side, it is U1 intersection U2 cross with V1 intersection V2, and of course that is a subset of U1 intersection U1 cross V1 intersection with U2 cross V2. And this is what we wanted to do. The second point for to show that something is the base. Hence, this should be, I don't know what yeah, strip B is a basis for a topology. Okay, and this basis is called, I mean, this will generate a topology. So the topology generated by generated by this strip B is called product topology on X cross Y. So remember that this is how we have defined this set. This set, if you have tau and tau as two topological spaces, the way we have defined this set, it is a basis for topology, and the topology generated by this basis is called the product topology. Okay, again, as usual, let me put this two, and then we can go for the next part. Okay, so let us take your x is same as y is same as r with usual topology. Let us take tau x is same as tau y to be usual topology. Okay. Now let us take tau p be product topology on r cross r induced by tau u, that is usual topology, maybe tau x tau y. Then tau p is same as Euclidean spelling Euclid just take spelling of Euclidean metric topology on R2. You know what is R2? R2 is R cross R. So here we are taking R cross R is the topology, and take the Euclidean metric topology on R2. And in that case, both the topologies will be same. Okay. Let me put one result for the basis for the topology and leave the proof of that as exercise. Okay, just you have to mimic the things what we have done till now. So result, let x comma tau x and y comma tau y, let's take two topological spaces be topological basis, and let script B1 and script B2 be their respective basis. Then the question is, what will be the basis for the product topology? X plus Y. Think, think, again think, and then come back. And you can then watch the video. Then D is equals to what will be the basis for X plus Y. We have basis B1 for X. We have basis B2 for Y. Then what will be the basis for X plus Y? Answer smartly, and then you proceed. This will be B1 cross with B2, where this B1 is the element of script B1 and this B2 is the element of script B2. So this is basis for product topology on X plus Y. As I said, good exercise. Okay, same thing what we have done. Right. Now, as the matrix spaces, when we have taken the examples of matrix spaces, then we define something. We have checked the theory for open sets, closed sets, limit point, cluster points, all those kind of things, and then connected spaces, compact spaces. So till now, I'm done with the basis, the simple basic definitions. I told you to check the definitions for covalent topology and prove that it's a covalent topology. Try to get the basis for covalent topology. Check what are the open sets in covalent topology, also countable topology, or other examples of topological spaces. Okay. In the next lectures, let's go for the theory for some results for the closed sets and limit points, cluster points, kinds of closure, interior, exterior, all those things we will check now. So see you in the next video.